In the signal flow graph, we will talk about the basic definitions, terminologies, different examples, and this, based on the signal flow graph, there is a particular rule we need to understand that is called Mason's rule. Mason's rule. We'll talk about that, and based on that Mason's rule, how we can solve the transfer function from any signal flow graph. We will talk about it, and we will talk about how we can reduce the block diagram. We can convert the block diagram to signal flow graph as well. So now, what is a signal flow graph? Signal flow graph, it is an alternate method. It is an alternate method of the graphical representation of a transfer function or some control system. We have seen transfer function. Transfer function is the mathematical representation of input-output relationship for any control system. Then we talked about the block diagram. What is the block diagram? Graphical representation of a transfer function for any control system. Graphical representation. Similar way here, the signal flow graph, it is also a graphical representation. Graph, the word here, the graph. Graph means it is also a graphical representation. So, it is an alternative method of the block diagram. Block diagram, it is also a graphical representation. Signal flow graph, it is also a graphical representation. So, we need to understand both different. This signal flow graph, this is developed by Samuel Jefferson Mason, very prominent scientist, along earlier, 70 years before he proposed this. Signal flow graph, it is consists of a network. In the network, where there are some nodes and branches. Nodes and branches. Suppose if here we have an example, y is equal to ax. We already know it is a simple equation. It is a simple equation. So, first of all, we need to define what are the inputs and outputs here. This is the output for this equation. This one is the input for this equation. And what is this? This is a constant value, or we can call it a gain. Gain. Now, we know how to represent it in block diagram. We know that, right? The block diagram representation, a rectangle block, we have x in the input side and y. So, that's the block diagram representation. Signal flow graph, it is also a graphical representation. So, how do we represent it? It is represented by some nodes and branches. So what are the nodes? The inputs and output, all are called the nodes. We have one input. So here we have a node. Then we have one output. That one we will call, it is also a node. So these are called node. Node. And then this signal, how it flows? Through a branch. The signal flows through a branch. And each branch will have one direction. All the branches are unidirectional. Unidirectional, one direction. How? Here, for this equation, the signal is flowing from x to y. The signal is flowing from x to y, input to output. So the direction is this, forward direction. So this one we call it a branch. Two nodes make a branch. Two nodes, x and y. Two nodes makes a branch, one branch. Not three nodes or four nodes, only two nodes. So here we have, and each branch will have a gain. What is the gain? This is the gain. So this one we know that this is called block diagram representation, what we discussed in our previous lecture, and this is the signal flow graph. Why we are calling it signal flow graph? Because look at this. The signal is flowing from X to Y with a gain A in forward direction. The signal is flowing from X to Y with a gain A in forward direction with two nodes where the nodes are X and Y, and the branch is this. The gain of this branch is A. So here you need to understand the gain. This is called the branch gain. We will need it a lot of time. Remember this. The branch gain. This is called the branch gain. It is explained here. You read it here. What I explained, it is mentioned here. So it depicts the signal flows from one point to the other and give the relationship among the signal. What is the relationship? Relationship y equal to x. That is the relationship. And here each variable we call a node. These are the variables x, y. These are the variables. So we call it a node, and this transmission function is designed by a branch. That is, two nodes makes a branch. And branches are always unidirectional, one direction. And the arrow that denotes how the direction of the signal flow. Suppose like this one, I will try to explain you. We have two equations. Two equations. Now, first of all, what do we need? I will write it here. Let's do it here first. I write y1 is equal to, I'm just ignoring s because it will be easier to understand. G11 R1 plus G12 R2. G11 R1, G12 R2, and Y2 we have two equations. G21 R1 plus G22 R2. Okay. Now, while you have a characteristics equation, some the other equation, differential equation, integral equation, any mathematical equation, first of all, you need to define the input and output. So what are the input here? What are the input here? R1 and R2. Inputs. We have two inputs, R1 and R2. And the outputs, Y1 and Y2. Now, you know about the input and outputs. Now you know how the signal is flowing. The signal always flows from input to output. The signal is flowing from in this direction, right? Okay, now we have two inputs, two outputs. So here we have one node, two nodes. These are for inputs, R1, R2. And we have two nodes for outputs, Y1 and Y2. Now, we need to draw the branches. Look, the branches. R1 is flowing to Y1. R1 is flowing to Y1. Here we have one branch. And what's the gain of that branch? G11. Second one, R2 is flowing to Y1. R2 is flowing to Y1. What's the gain of that branch? G1, 2. Similarly, y is the output for the second equation where R1 is flowing to Y2. R1 is flowing to Y2. We have the direction. We must need to provide the direction. R1 is going to Y1. R2 is flowing to Y1. So the direction is in that direction. Now R1 is going to Y. R1 is flowing to Y2. The direction is this, and the gain is G21. And then R2 is flowing to Y2, and the direction is this, with the gain of G22. This is the signal flow graph for these two equations. Signal flow graph. It is a graph where it will show how the signal flows. The definition is the signal flow graph is like that. So we have the signal flow graph. Let's do another one, third one here. Now we have, it is mentioned that R1, R2 are the inputs here, and X1, X2 are the outputs. So how can we draw it? R1, R2 are the inputs. That means here we have two inputs. Then X1 and X2 are the outputs. Here, X1 and X2. We have two more nodes. Now, how the signal is flowing? Look, the signal is flowing R1 to X1. Here, R1 to X1. And the direction is this direction. What is the gain? It is 1. Because R1 we just have nothing, so it's 1. Second, X2 is flowing to X1. Where is X2? Here. X2 is flowing to X1 in this direction with the gain. What's the gain? A12. A12. Third one. X1 is flowing to X1. X1 is flowing to X1. That means here X1 is flowing to X1 with the gain A11. This is called self-loop. We will need it, remember the name. This is called self-loop. Self means its own loop. It starts from the same point, same node. It is ending in the same node. It is starting from the one node and it is ending in the same node. That is called self-loop. Self-loop. If there is only one point, starting and ending at the same point, then we call it self-loop. Alright, now the second one. Here, the R2 is flowing to X2. R2 is flowing to X2. And this is the direction with a gain of 1. Second one, X2 is flowing to X2. Again, X2, it is started from here, it is ending in the same. That means it is also a self-loop with a gain of A22. This is also a self-loop. The third one is X1 is flowing to X2. So X1 is flowing to X2 here. X1 is flowing to X2 with the direction, downward direction. with a gain of A to 1. So that's another signal flow graph for these two equations. That's how we draw the signal flow graph for different equations. Understood? It is much more easier. This part is much more easier. But later on we will have a complicated one. These are very simple equations, very simple. That's why. But first you need to understand the signal flow graph first. Here we have the signal flow graph for this. Here A21 and A12 it is mentioned in the another direction, but the direction are the same. So you can provide any, but the direction has to be accurate. Downward, upward has to be the same. Alright, now let's do another one here. We have another equation. Now we have 4 equations. Before we had 2 equations. Now we have 4 equations. And each equation we have input, we have output. Each equation we have input, we have output. So you must need to define first about the input and output for each equation. Okay, now it is a successive equations, like it is started from x0, then x1, then x2, then x3, then x4. So the initial input is x0, final output is x4. Initial input x0, final output is x4. Okay, how can we draw it? Let me see. This is initial input, and here this one is final output. But in each equation we have input and output. The signal will flow from input to output. The signal will flow in these directions. So for this equation, we have input already, we know. So here we have this, what we mentioned, x0. The final output here, it is x4. Now, in the between there will be some other variables. We have first here, that is the first output. So x0, how it is flowing? Look at this. It is flowing to x1. So here we have one more, that is x1. Okay. So x0 is flowing to x1 here. The direction is polar direction with a gain of a. With a gain of a. Second, x1 is flowing to x1. Again, same loop. That is called self loop. Same loop, self loop. So x1 is flowing to x1. That means here we have x1 is flowing to x1 with a gain of b. And x2 is flowing to x1. That means it is not from input to output, it is in backward direction, reverse direction. Here we have x2. X2 is flowing to x1. So this is in forward direction, it will go forward. So it cannot be here. It cannot be here. It will be here. Because the direction, it is backward direction. Backward. Because x2 is flowing back to x1 again. x2 is flowing back to x1. So x2 is flowing back to x1 with a gain of c. Because it is a forward one, and backward feedback. This is called feedback. Now, second one, for the second equation. Now what is the input? This is the input. x1 is the input for the second equation. This is the output for second equation. So the signal is flowing from x1 to x2, from x1 to x2 with a gain in the forward direction. It is a forward direction with a gain of d. With a gain of d. And later on, here you see x3 is flowing to x2. Now here we have an x3. We need to define x3. Now x3 is flowing to x2. That is not forward direction. It is backward direction. Backward. That means here. Feedback. x3 is flowing back to x2 with a gain of e. So it is backward direction. Now that's the second equation. Now the third equation. What is the third equation? In the third equation, x0 is flowing to x3. So look at this, x0 here, x3 there, forward direction here, forward direction, forward direction. x0 is flowing to x3 with a branch name f. And x2 is flowing to x3. It is just a forward direction here. We have a forward direction here with a gain of g. G. Simple. Now the last one, x3 is flowing to x4. x3 is flowing to x4 with a forward direction with a gain of h. So that's all the signal flow graph for all the four different equations that we have here. Remember how the signal is flowing. So if you see the signal is flowing back, that is feedback, reverse direction, backward direction. If it is going in the forward direction, like from x1 to x2, that is in forward direction, that you must need to define it. And here, look at this part, one part will have one direction. We will talk about the part later on. Why I did not use this part for this? Why I did not use this part for this? I will explain. Why I did not use the backward direction here? Why I did not backward direction here? I'll explain it later on. So that's how we actually draw the signal flow graph for any equations. Now we will discuss everything. First of all, the input node. Input node, we call it source. Source. Where the signal will start, that is called source. Input, we call source. Here, this voltage, this is the voltage, plus minus Vs. This is current, Is. This is called the source in electronics. Input, these are the inputs. Voltage input, current input. These are called source. Electrical source, mechanical source, any sources are there. So all the sources are input. So input contains only the outgoing branches. What are the outgoing branches? It starts from here. There is no branch before that. Before there is no branch. After that there are branches. That is called outgoing branches. And the output node here, this is the output, final output node. Final output node contains all the incoming branches. What are the branches? Two nodes makes a branch. Two nodes make a branch. So here, all the branches, look at this, two node, two node, two node. Here there are two nodes. All are the incoming branches. Here, it is coming, incoming. So next is called path. What is a path? Path is a continuous, unidirectional succession of branches. Path. If there are more than one branches, If there are more than one branch, multiple branch makes a path. 2 branches makes a path. 3 branches make a path. So if there are 1 branch, that is not a path. If there are 2 branches, that will make a path. 3 branches, that will make a path. Here, x1, x2, x3, x4, it is a path. Second one, x1, x2, x4, it is a path. Last one, x2, x3, x4, that is also a path. Now, what is common here? First thing, it is unidirection, one direction. Look, forward direction, forward direction, forward direction. Here, second one, forward direction, one direction. So before it is also forward direction. So a path will have one direction, and second, it will have more than one branch. Here, how many branches? 1 branch, 2, 3 branches. Here, how many branches? 1, 2 branches. Here, how many branches? 1, 2 branches. So a path will make if there are more than one branch and if there is one direction. So this is why you saw here I did not include this one here, this feedback here. I did not include this is here because this is a path and path will have one direction. If I use this, if I use this one here, see, it would be wrong, right? Because it is a path, it has to be one direction. It is backward direction, it is wrong. Here, if I use this one here, E, it is wrong. Because a path has to be one direction. So that's why it is drawn here like this. So a path is unidirectional. A path will have more than one branch. Alright, now that's a path. Now there are 2 types of paths. One forward path, another one feedback path. Forward path, what is that? A forward path is a path that will start from an input and it will stop to the output. Look, this forward path, x1, x2 to x3 to x4, here, x2, x3, x4, starts here, stops here. The path starts from the input, stops at the output. So a forward path will be a path which will start from an input node and it will stop at the output node. From input to output, the whole path. So here there is one more. Look, x1, x2 to x4. x1, x2, x4. Here, this one. Again, it starts from the input, stopped at the output. So there are 2 forward paths here in this example. 2 forward paths. Let me tell you here. Let's see this example. In this example, how many forward paths here? Anyone? How many? 1 or 2? 1 or 2? 2. 2 forward paths here. How? One is this x0 to x1, x2, x3 and x4. And there is one more here. It is forward direction, x0, then what? x3, directly x3, it is going to x3, and then x4. Now, how do you measure the gain for this? We will talk about the gain later. Let's see about the forward path. These are the forward paths. Two forward paths in this example. One is normal one, and it is another one. Now the second one, it is the feedback path. Feedback path we call, if it starts from a node, it ends to the node again. Suppose here, a feedback path which originates and terminates on the same node. Originate means started, and it stopped, it terminates in the same node. So here, look at this. If we talk about this, it is going forward direction, then it is going backward direction. It is a feedback path, right? So here x2, x3 and x2, x2, that is a feedback path. So in this example, do we have any other feedback? Look, if we talk about this, x2, x3, x4, is it feedback? Is it feedback? Look, forward direction. This is forward direction. Is it feedback? No. So we have only one forward path in this example. So feedback path does not need to start from input. It will start, but it will start from a node and it will end up in the same node. It is started from x2, going to x3 and ending up at the x2 again. That is feedback. Shortly we call it loop. That is a loop. Let's see. Previous example here. Look at this. Here. In this example, we have here. Look at this. It is starting from x1 for a direction, and it is going back to x1. So here this is a loop. Loop 1. Here, 1. Another one, look at this. It is started from x2, forward direction, going back to x2 again. Loop 2. Any other? Here, look at this. Look at this. It is going forward direction, x2, 0, x1, x2, x3. Is it? No. Don't. This is not a loop. So we have two loops. Feedback loops. One, it is x1 to x2, coming back to x1 again. Second one, x2 to x3, coming back to x3 again. So here it is x1, x2. Here, back to x1. Loop 2, x2 to x3, back to x2. So we have two loops, feedback loops. So we know how to find forward loops, feedback loops. Important, very important, because in the later on we will need to find it out. We need to find out the gain. That's why we need to find out the feedback and forward loops. Feedback path and forward loop, feedback loops. So now the next one is the self loop, I already told you, the self loop, it will start from one point and you will end up in the same node. You will start in this one node, it will end up in the same node here. There is only one node. That is called self loop. Now why we need to find out these loops? Because we need to find out the gains of these loops. Gain. I already told you, look at this. Gain. Branch gain. What is the gain? A. So we must need to find out the gains. That's why we need this. Now, what are the gains? Gain is the product of all the branch gains. Gain is the product of all the branch gains having in that forward path or feedback loop. So path gain is for forward path gain, and loop gain is for feedback loop gain, feedback paths gain. So let's see here, what are the forward paths? We have two forward paths. One is started from x1, x2, x3, x4. So here, what are the gains? Path gain, that is we can call it forward path gain. So forward path gain, look, started from here and in here. So how many gains we have? A1 2, A3 2, A4 3. So we have A1 2, A2 1, A3 2, and A4 3. That is the gain. That is the gain. All will be multiplied. All the gains will be multiplied. All the branch gain will be multiplied. Branch gain, each gain here. Branch gain, each branch will have a gain. And all the gains will be multiplied in that path. Second, the loop gain. What is the loop gain? Feedback. Feedback path gain. This is path gain, we call it forward path gain, and feedback, that is called the loop gain. Now, here we have one more forward path, right? One more forward path. Here, this one. Started from x1. Here we have x2. Then we have x4. That means two branches. And 2 1 and 4 2. So there is one more path gain. One more here. This is 1. And one we have one more. A2 1 A4 2. And 2 1 A4 2. We have two more. Two path gain for our path gains. So one is A2 1 3 2 4 3, and another one is A2 1 4 2. Here. Here we have two forward paths. So here it is mentioned only one, but we have two path gains. So you must need to define that as the next one, the loop gain. So how many loops we have? We have one loop, that is x2 to x3 and back to x2. So the loop gain, that is the feedback loop, we have x2 to x3 back to x2. We have two gains, so it will be a3 to a3, multiplication of a3 and a3. Now, there is one thing, one statement you need to understand, that is called two loops or paths are say non-touching if there are no common points, no nodes in common. Like look at this, here we have one node, one loop, so we cannot call there is a non-touching loop. So we need to find out if there are two loops in any example. Let's see. First of all, here we will find out path gain. Path gain in for this example. How many paths? 2 paths. So what is the first one? This is the first one. And what is the gain for the first path gain? First path gain, it is x0, x1, x2, x3, x4. So the path gain is ADGH. ADGH, that is the path gain. First path gain. Second path gain, there are 2 paths, we already know. Another path here, this is another path. It is x0 to x3 to x4. So here x0 to x3, that is f. The gain is f. And x3 to x4, that is h. These are the 2 path gains. The second, loop gain. How many loops? 1, 2. 2 loops. 2 loops. So, first loop gain. What is that? First loop gain. x1, x2. x1 to x2, back to x1. Back to x1. So, this one, what is that? D into C. Second loop gain. Second loop gain here. x2 to x3, back to x2. x2 to x3, back to x2. What is the loop gain? G, E. Multiplication of G and E. These are the path gain and loop gain for this example, for this signal flow graph. Now, what we need to understand the non-touching loops. Non-touching loop. What is the non-touching loop? I said that we call 2 loops are non-touching if there are no nodes in common. Look at this. We have a loop here. Here we have another loop. Here we have a common point. Common. This is the common loop. I said we will call non-touching loop. There will be a non-touching loops if there are no nodes in common, but we have one common node. So here, no non-touching loops. No non-touching loops. A loop. Because we have a common point, we have 2 loop. So we need to find out the non-touching loop for this. But here we have a common point. So if there is a common point for this 2 loop, then we will call it does not have any non-touching loop. So no non-touching loop. We will need the later on. Let's see. We will do the example later on.